Okay, so now what I'm going to do in this video is show you how to solve a circuit where you have a combination of both parallel and series. And not only that, be able to figure out what the voltage and the current is for each of these resistors right here. So part one of this video is I'm going to solve this in detail, and then part two I'm going to solve two other ones. So this is more about the theory, and then the other ones I'm just going to kind of completely solve. So, like we've been talking about, we've been using Ohm's law for a very simple case, but now when we have more advanced circuits, we can't just use Ohm's law. It doesn't work. If I say, what is the current over here? Well, I can't just use V equals I over R roughly because of the different properties of them, remembering that these are the same voltages and these are the same currents because this is series and parallel. But now we're going to have cases where we have both parallel and series circuit. Let me explain. I think visually, if I were to cover up R3, you would see that these two would be in series with each other if we ignore this one, right? But if we ignore R1, then we see that these are in parallel. So R1 is in series with the parallel circuit. Therefore, these are not the same as analyzing these. We have to use different rules. We can't just solve it out. So I'm going to show you how to recognize, when something's in series and in parallel, and then how to solve these out as a complex circuit. These are notes from the previous one. I'll let you read them on your own. They're pretty straightforward. But remember, series and parallel circuits. A note on energy I didn't discuss earlier. So what you have here is an animation that shows you what the energy is like in the circuit. And the energy is represented by the three-dimensional case here. So I'll call this the z-axis right here, and this would be the x and the y. So as you can see, this right here represents a place where the energy increases. This will be our battery. And this is what it does. It takes the charges and moves them up. It gives them a lot of energy. Now as they move through the circuit, they'll pass through a resistor. Now what would happen is they take some of that energy and they use a windmill to explain that some of that energy goes into pushing that windmill. In other words, it goes out into another source. So it loses energy. So if you notice here, this actually decreases. We lost energy. And we lost quite a bit of energy in comparison to the 10 ohm. Notice how this is a steeper slope than this one. This has lost more energy. As a circuit, this would be a light bulb. And this one lost more energy, so this one's going to be brighter. So this one right here, notice that it has less energy to work with. So this one will, once again, go down and take some of that energy away. And then notice we're back down at the bottom. And what the battery does, it gives it its energy again. So a couple things. Number one, this is conservation of energy. Notice that whatever energy we start with, we end with. So if we start with this amount, we give it to these two devices and we end with it. And also, conservation of charge. Notice that if we were to count these, we will not, but if we counted any of these, the number would be fixed. So if there are 50 charges in the system, it would always stay 50. Now notice that they're talking about positive charges. The definition of current is actually the flow of positive charges. So that's why they're using positives here. But yes, you are correct. If you're saying that isn't it electrons that are moving, you are right. But by convention, we always talk about it as the positive charge. So we did this in the previous example in class, so I'm not going to solve this out. I'm assuming you're pretty comfortable with these. So these are just some extra questions, and those are some values if you'd like to try it out. Same thing with the parallel circuit. You notice the energy distribution and the way it's treated is different. Just taking a quick step back, conservation of charge is still the same. We don't lose any of our electrons, and if we watch this for hours, we would see, the same amount. None of them get lost. We don't add extra ones. The amount of the electrons that are here stay the same. So if we look at it in a sort of an energy perspective, what we'll find is that you'll see that the energy drops for each of these are the same as the energy that is given by the battery. So that's the whole voltage is the same kind of thing. So as this falls down, you could see that these cases, in both of these cases, have the same energy drop or voltage drop is what we'll say. And notice this one's easier to push. So more current will go through this. You can see the more charge per time. For this one's harder to push. So you see less charges go by in this per time. Therefore, the current here is way less than the current right here. But if we were to analyze the motion, they would all equal out in the end. In other words, this current here plus this one equals that. So again, in the AP, they like to know if you understand the energy relationship between these types of circuits. Okay, and again, these are all sample problems for resistors in parallel. I'm going to be using these to help us reduce or get the resistance equivalence of something like this. In fact, let's do this one. So what I'm going to do is solve this completely. I'm going to find the resistance equivalence, and then I'm going to find the voltage and current in each of these branches. So why don't we start that? So the main approach, and of course there's no step-by-step because unfortunately they are all different, which means they will require different steps. But the general idea for each of these is that I'm going to look for sections that are completely parallel and completely series and break them down. So if they're a part of another section that is a different circuit, we can't break it down. So, oops, let's go this way. So what do I mean by that? So if I started, what I'm going to do is try to group some of these resistors here so that they make a series or parallel. So let me show you the difference between starting here and starting here. So if you notice, the 8, 20, and 12, if I were to cover up this 40, is in fact all in series. They're all connected the same way. But I can't include this one. The reason why is because this one is seeing the same connection of one side of the resistor right here. This is actually in parallel with this. In fact, the correct thing is to say the 40 is in parallel with the 3 of these. So I can't include this in my series because it's not completely series because of this junction right here. Same thing. I can't start here because if you notice, if I try to make this a series circuit, which looks like pretty much like a series right here, this one is connected in parallel because of that junction. We have a place where the charge could, basically have a choice. Therefore, this and this are not in series with each other, so I can't start here. Where I'm going to start to break things down is actually right here, because as you see, if I ignore the 40, these are actually all connected in what we call series. So with that said, I gotta turn this on, sorry. I'm going to pretend or find the resistance equivalent of just these 3 right here. So if I do that, it's going to be 8 plus 20 plus 12. Sorry, my thing went off. So 8 plus 20 plus 12. That gives us a 40 ohm resistance here. So what I'm going to do is kind of like squish this down into one resistor that represents the 3 of them, just like we've done before. And what we're going to do that is call the 3 of these the 40 ohm resistor right here. So if you look in the next slide, notice that I reduced this down to the resistance equivalence of the previous one. So the previous one had 12 plus 8 plus 20. That gave me 40. That's where this number came from. So now that I broke it down, I could see that these are in complete parallel with each other. Again, I'm not including this one because this one's actually in series with this. But these two are in parallel, which means I could squish these two down into one resistor by doing the parallel resistance equivalence. So the inverse of 40 plus the inverse of 40 gives me 0.05, but I need to take the inverse of that, so I'm doing 1 over REQ, remember. So REQ has to be the inverse of that number, which gives me 20 ohms. So between this one and this one, notice that I quote, in the slides, I'm purposely redrawing the circuit as you should as well, as you solve these. It's the same as writing this one as a 20 ohm circuit. Now you can see there's no other resistors in here, and these make one loop, therefore this is one series circuit. So you can see it right here. And then as you know, with the resistance equivalence, I can again squish this down. They are going to add because they're in series. So this circuit looks like this circuit, where this one we found was 40, right? Just want to double check. Oops, sorry. 2020 is 40. Okay. Yeah, I was right. Okay. Goes back to 40. So we found the resistance equivalence. We solved part A of the circuit is 40 ohms, just like that. So basically what I'm going to do is kind of go backwards to find each thing, because at this point, it's the only point we could find the current in this battery. So current is going to be equal to V over R. So our V is 12 volts, our R is 40 ohms. 12 divided by 40 gives us 0.3 as our current, amps, just like that. So as you might imagine, that tells us that this will be 0.3 amps. How do we go from here? So we went from this to this. Remember, our back step, if you will, was here. So between here and here, we were series circuits. What we can say is, if we want to know what the voltage is between these two, we know that this was a series circuit, and this is not a series, but more or less. We can use the fact that this is one loop, and this is one loop, and say that these currents are actually the same. I is 0.3 here, and I is 0.3 here. And this is because series. So I was stressing in class that series has the same current. This is where it's very helpful. So the V right here, I'll call it 1 and 2. V1 is going to be I1, R1. I1 is 0.3, R1 is 20. So I have the voltage for this, 6 volts. Now V1 is 6 volts. I can figure this out, but if you notice, these are the same numbers, so this will also be 6 volts. Or I could have said 6 volts, the total has to be 12, so this must be 6. So that's another way you can solve this in a kind of quick manner. What I'm going to do is actually stop here because my video is going to end. I'm going to continue this in part 2.